we have considered the activity model under two different dissipation. We are using the infinite time evolution of blood decimation. Is a method introduced by Vidal some years ago, I think 3 years ago. And with this method, we time evolve in the imaginary time around the initial wave function. And we expect for huge times, we projected out the ground state of the system. And this method can be adapted for open quantum system, where now we have two steps. The first step is the time evolving the wave function that we want to project the ground state. When you project out the ground state, we construct all these two matrices in time zero. And then we apply the real-time evolution from the activity adapted code for the open quantum system and solve the Lindblad-Nash equation until we consider one convergence criterion. For us, the convergence criterion is when you reach the equilibrium state is when the density matrix stops to evolve. So we expect we apply the Lindblad operator in the density matrix in the equilibrium state. This one is zero, right? So in the vectorized form, we can define the parameter delta. Right in that way, when V delta is equal to zero, we reach the no equilibrium state. So this is the criterion that we are using here. Okay, we reach the convergence. Now we can proceed to our calculation. And here we are considering first two different dissipation, SZ and SZ squared. So especially we are considering this dissipation because the one dissipation is not symmetric in respect to the Hamiltonian system. And SZ squared is symmetric. So what happened when we consider a symmetry-protected topological order first with a non-symmetric dissipation and then with a symmetric dissipation. So we start from non-symmetric global dissipation. So here global is because each site of the system in the thermodynamic limit have one dissipator given by SZ. And we using this in the Lindblad-Nash equation is solving it. So first, here we're starting with the non-symmetric dissipation. Here is the delta parameter for 10 values of the dissipation parameter gamma. Start 0.1 until 1.0. So in the y-axis we have the parameter delta is all convergence criterion parameter. In the x-axis we have the time, and we see for all the 10 values of the dissipation parameter, all delta parameter goes to zero. The time goes to 100 time steps. So okay, we are reaching the equilibrium state. With that in hand, we can follow to our measurement. So first, here's the measurement of the SZ squared in the low equilibrium state. So, in the equilibrium state is the evolution of this quantity until reach the equilibrium state. And we see even for the tiniest value of the dissipation parameter, we saw this quantity going to zero. So yes. This reflects there is don't look like have anything special happen in the XZ axis. Here we can compute the SX, SY, or SZ quantity, but still zero in all simulations. So because that I don't put here. So what about the string order parameter? So we consider the string order parameter for SX, and as we expect, this quantity starts finite in the time zero. Because the actuality ground state is a topological order. So this quantity is finite. And when time evolves, this goes to zero for all values of dissipation parameter we consider, even for the lowest one. So for the x, y, we expect the similar behavior because the symmetry of the system in these two axes. We have a really similar behavior. So the string order parameter again. We have the string order parameter in the y-axis, the time in the x-axis. We have this both quantities going to zero for all parameters, all dissipational parameters we consider. So, and the string order parameter for SZ also goes to zero. Okay. So we see, okay, don't look like having anything special happening here. So you really, okay, this kind of dissipation looks like destroying the topological order. But we miss one thing. What about entanglement spectrum? Again, when we consider entanglement spectrum of a topological order, we expect we have doublets, degeneracies in this quantity. So here we have the entanglement spectrum of the non-equilibrium steady state for the 10 values of dissipation parameter, which is 0.1, 1.0. We have just one point here, just here we have two constants, but we don't have any different behavior along all this huge space parameter we consider of the dissipation parameter done. So okay, it looks like this kind of dissipation as destroy the topological order. It will evolve in time. Okay, so again we get 0 string order parameters in the 3 string components, and we have 0 entanglements, and we have no doublets in entanglement spectrum. In the entanglement spectrum. What about this squared? Asymmetric dissipation. Okay, again, just on convergence criterion, we compute the delta parameter for all the 10 dissipational parameter we consider. Now the dissipation goes to 0.05 until 0.5, and we see for this 10 values of the dissipation parameter, all the values go to 0, and we reach the equilibrium size. Okay, the SC squared, now we have a different behavior. It goes to 1 in the equilibrium state. For all values of dissipation we consider, even the tiniest one, we have this quantity goes to 1. Okay, looks like we have something happening. From now the string order parameter for xsx, again we have this quantity goes to 0 when we reach the equilibrium state. For all values of the dissipational parameter we consider, we expect the same thing for xy because of the symmetry of the system. Again, the string order parameter using this operator goes to 0, the equilibrium state in sign. But okay, the string order parameters for sz goes to 1. Well, maybe you have something happening. Even for the tiniest value of the dissipational parameter, we have something converging to 1 in the equilibrium state. So what about, let's see what the behavior of the local magnetization in some values, some selected values of the parameter, the dissipational parameter. Here, for example, we have the time evolution we separate the system in two sublattices, A and B, and we see how the local magnetization in the z-axis evolve in time, start in the alkalinity model at t equals to 0, in the low equilibrium state, when the time evolution the time growth until 200. And we see clearly from this value of the dissipation parameters, 0.2636, we have a kind of something like a Nel antiferromagnetic order, induced by dissipation. I have to say that. Here we have something like dissipative antiferromagnetic phase. For 0.2637, we have the similar behavior. Again, we reach the dissipative antiferromagnetic phase, but for values higher than that, we don't have any local order in our system. The both SC A and SC go is strictly 0 in all for all values of higher than this dissipation parameter we consider. Again, for 36 and 9 we have the same. For all values we consider is strictly 0. So what happened here? We have looks like a phase transition. We had before something like a dissipative magnetic phase. Now we have no in the order. But remember, we saw that the string order parameters goes to a finite value in the equilibrium state. So what about the entanglement spectrum? What we have? Okay, here we have the entanglement spectrum for some selected values of dissipation parameter going to 0.2638 to 0.2646. And here we have the similar behavior we saw before. we have no doublets in this phase, but here we have antiferromagnetic phase, a dissipative antiferromagnetic phase. And now, beyond some critical dissipation parameter, we have doublets appearing in all integument spectrum. This is a signal of a topological phase, but now we have a dissipative topological phase. Topological phase induced by dissipation, by symmetric dissipation. And this looks like a dissipative topological phase transition between this Nel order phase and this topological phase. And this, we are now checking how we can, what kind of topological order is that? The Holden phase is a different form of an equality state. So we, with the string order parameters in the integument spectrum, we don't have this answer yet. So again, this is just our preliminary results. So here the main results in our conclusion is, again, we consider a hyperactive model in the thermodynamic limit, considering a symmetric dissipation first, and a non-symmetric dissipation first, and a symmetric dissipation later. And we see for non-symmetric global dissipation, we obtain a non-topological order, disordered topological order. And when we consider a symmetric dissipation, we have two phases, one dissipative antiferromagnetic phase, and another dissipative topological order, separated by the dissipative topological phase. And now the question is, what kind of topological phase we get? Is it still a symmetry-protected topological phase, induced by dissipation? And if this is true, how we can, this phase is protected by what symmetry? So now right now we're trying to use the topological index from the closed quantum systems to try to compute. We are seeing if you can use this kind of measurements to compute the topological order for open quantum system. And what kind of is that dissipative phase transition? For which universality class you can maybe check the critical exponent. This is all the questions we are reaching and searching right now. And that's all. Thank you, my department. CAPS, we have the pay account. And then the National International Physics Center, we hosted the last 6 months last year. Thank you.
Okay, Luan, thank you very much for your presentation. Now the discussion is open for questions and comments. Are there any? Give me just a second. Okay. Joseph has a question. Please come here.
So my question concerns with spin 2 Heisenberg chain, which also show Haldane phase, but which much smaller Haldane gap. So there is a gap which is maybe 4 times smaller with respect to spin 1 chain. Can you estimate what will be the effect of dissipation for such kind of non-trivial quantum state, topological non-trivial quantum state, which has much smaller gap?
Yes. This will be the next idea that we're working on. When homologous actually have a paper, when we consider the spin 2 system with the exchange interaction to the 4th order, and there is a statistical journal. There's a paper in the spin journal who shows for a specific value of K0, 1, 3, we can have a symmetrical quantum phase. There's a homologous and another auto explorer. The phase diagram of this phase. And he demonstrated there that we have the SO5 Haldane phase, intermediate Haldane phase, the large B phase. So here, for this model, that the spin is exactly what I said, the spin gaps in the S1 hyperbolic model. And it's much more interesting because we have 4 atomic generators of the symmetry group for this model. And we have actually 4 symmetric dissipation. So yes, we are looking for the model as a perspective of the next one. But we are using the identity model as a basic idea to understand exactly what we're doing, this kind of things, and then go forward for this second model.
Yeah, thank you very much.
Okay, Andreas has a question, so please go on.
Yeah, Thank you. So actually, I have a philosophical question.
Sorry?
You might have to switch the mic in order to eliminate the echo. Okay, so the question that I have is philosophical kind of.
Give us a second. Just
Okay, so it's a bit of a philosophical question in the sense, what is dissipation? So if I saw correctly, you actually coupled Lindblad operators to their Z, but how generic is that? For example, if you instead of coupling to the local spin, you couple to the energy density, would this change things? Do you have any idea?
Sorry, can you repeat, please?
So the question is, you had a specific type of dissipation by coupling Lindblad to their Z operator. If you couple, if you do a different dissipation, couple to different operators, for example, energy density, spin-spin correlation, would it have the same effect? Do you have any idea how generic this coupling is?
To be honest, I don't know. We don't try to, at least in this first article, we don't try to see what happened from this kind of measurement of correlators or the energy density, consider a different kind of dissipation. Not right now. But,
Okay.
I can answer this right now.
Okay, thank you.
Thank you.
okay. Onofre has a question. So Onofre, please come closer to the mic.
I guess it's just maybe I didn't pay attention to your presentation. Maybe you just tell me about this plots, your plots relating the time. There is this follow some kind of yes, asymptotic expression you have, but previously maybe there are several plots you have something like exponential or something like that. This follows some kind of functions like exponential or something like that.
That's a good question. Actually, we have to double check if this, if for example, if we consider the staggered magnetization on this kind of neo-antiferromagnetic order, if this quantity, how this quantity goes to zero? It's going to zero continuously or goes to zero as a first order phase transition, right? Or what kind of load is going to zero exponentially or parallel? Yeah, we are looking exactly like that to try to characterize this dissipative topological phase transition. This looked like I saw similar behaviors for closed consistent between a transition between antiferromagnetic Neo order and the Haldane phase. This quantum phase transition from the easy universality class for a closed consistent. There's really similar behavior. But right now, for the open quantum system, the thing is quite different, and I don't know exactly how we can characterize this phase transition.
Okay, so let me check if there are some online questions. Not yet, not more questions here in audience. Okay, Rodrigo has a question.
Okay. Yeah, you mentioned at the beginning that the Haldane phase is protected by a set of symmetries. You just have one instead of. And then your first dissipation term, that's the growth time reversal. But I guess it still preserves some other symmetries like bond inversion. Do you understand why it destroys the Haldane phase? It's like this dissipative topological phase requires more symmetries to be protected, something like that?
Yeah, this is why we have to using the topological order measurements to see what's happening in the first case and the second phase. The first case, I know this kind of interactions broke also the time reversal symmetry. I think also the dihedral group symmetry is also a symmetry who protect the Haldane phase. So I think this dissipation, non-symmetric dissipation, broke these two symmetries. So from the second part, when we consider SZ squared, SZ squared preserve the dihedral group, but and don't break the time reversal symmetry. But we have to see from the second part which kind of symmetry remains is protecting this phase, if this phase is protected by any specific symmetry. This is why we are trying to focus to calculate the topological index from this phase using the matrix product states structure of the tensor network to compute the topological index and see what is happening. That there's an article from Frank Pullman again, where he shows we can explore the injectivity of the matrix product states to see if one specific symmetry which is represented for operator is protected or not in that phase. This is idea we are trying to catch in the closed system and try to apply in the open quantum system to see what's exactly going on. Even the first case, because again, all this kind of structure that this kind of properties that I described, if for the closed quantum system, for open quantum system, this is quite open question yet. Maybe the first case where I discussed with Professor Roman and Marcelo, those look like a topological order. Maybe, as you say, maybe can be protected for another symmetry, or have to be described by another topological index. And we are trying to answer this question with carefully, because everything is new. I don't remember it so in the spin systems and in dissipative or any topological order induced by dissipation. So we are really going slowly in all these details to understand exactly what's going on.
Okay. I do not see any more questions, so thank you very much again for the